Okay, time for some more discussion about topics from Chapter 6. What we need to work on next is understanding molecular and empirical formulas, which is objective number 9 on this list. Determining the molecular formula of a compound from an empirical formula and a molar mass, and percent compositions and empirical formulas. These are all interrelated, and they're from section 6 of the chapter. Okay, so talking about percent composition, what are we talking about here? Well, it's expressed by figuring out the elements present and giving the mass percent of each. In other words, how many grams out of 100 when we're talking about percent. The empirical formula is how we commonly describe ionic compounds, but it's a smallest whole number ratio of atoms in a compound. This can apply also to molecular compounds at times. Molecular formulas are actual numbers of atoms in a molecule, so it refers specifically to molecules. And it can be either the same as the empirical formula, or sometimes it's going to be a multiple of the empirical formula. So if it's a multiple, you can use the molecular weight and just divide by the empirical formula weight to figure out what that multiple will be. Advance the slide. So let's take an example here. We have a colorless liquid given that someone has told us the composition is 84.1% carbon and 15.9% hydrogen by mass. And from that, we are asked to determine the empirical formula. Secondly, from this information as well, given a molar mass of the compound to be 114.2, you could determine the molecular formula of the compound. Okay, so what we have to do is we start off with the mass percents, which are what we've given in this statement here, for the carbon and the hydrogen. And then we'll use them to determine the numbers of moles using molar masses as your conversion factor. And then you take a ratio of the moles of the two substances that are in your compound and determine a relative mole ratio to give you the subscripts of the compound, the components of your empirical formula. Let's see how that works. So if we have 100 grams of the substance, that's what we do when we're thinking in terms of percent. That's per 100 grams. If you had 84.1% carbon, then we can determine the number of moles of carbon in 100 grams. And so there's going to be 1 mole of carbon for every 12.01 grams. And that's the usual number right off the periodic table. Notice that if you set this up carefully, the units will cancel. And as it turns out, this one is a very clean-looking value, 7 moles of carbon. And the moles of hydrogen, you take the number of grams from, assume like the percent. In other words, this 15.9% that we were given in this problem. Then we take that number of grams as how many you have in 100 and divide by the molar mass of hydrogen, 1.008008. Divide by grams per mole, and you get the number of moles of hydrogen. That gives us how the ratio of the two elements are combined on mole per mole basis in the compound. So what do we do with it? Those two values provide for us an empirical formula, but we don't want to use funny fractions. So what you do is you think about it as carbon with 7 and hydrogen with 15.8, and then you divide those subscripts by whichever value is the smallest value in your ratio. So divide them both by 7, and now you get a different set of subscripts. Well, at least one of them is an integer, and the other one is not. And so you have to fiddle around with it a little bit to come up with whole numbers, and sometimes it takes some trial and error. And so if you play the numbers a little bit, from the 1 and 2.26 subscripts, what can you multiply it by that would end up with whole numbers? Multiply the 2.26 to get whole numbers. It can't be 2, it wouldn't be 3. Turns out that 4 times 2.26 comes out to mighty close to 9. And so this is in fact the empirical formula for this compound in our unknown substance. Now, given the information previously that the molecular weight was 114.2 grams per mole, what we have to do is figure out whether this C4H9 is going to correspond to that or not. So what you do is you calculate the molecular weight of just this empirical formula, so 4 times carbon, which is essentially 12, and 9 of hydrogen, which is essentially 1. So if you take 48 plus 9, that should give you 57. For the simplest empirical formula, it's 57 grams per mole. Well, it's not necessarily the molecular weight because that's only the empirical formula, the mass of the empirical formula. So what we're doing over here is we're determining that the molecular formula has to be a multiple of the empirical formula. The molecular is a multiple of the empirical, right? And so if you take the molar mass that's given, grams per mole, right, and the mass of the empirical formula, it comes out to be a ratio of 2. And so you take all those subscripts and multiply them by 2, and the answer turns out to be C8H18. Hopefully you can use this type of strategy on other questions that look similar to this. So here's another example. This one has more parts to it, and it'll take us longer to think it through, but that's OK. Sometimes you need to see examples that have more challenge to them. OK, so ibuprofen, we've all heard of that. Most of you have taken it for something for pain relief. And it has a composition that includes carbon, hydrogen, and oxygen. Their percentages are given here. It's this much carbon, this much oxygen, and this much hydrogen by mass. And first we're asked to come up with an empirical formula. And once we've done that, we'll determine, given the molar mass at 206.3 grams per mole, we'll figure out, secondly, but not on this screen, the molecular formula for the compound. OK, so again, we'll use the mass percents that are provided in the question and with molar masses to come up with the moles of each substance in 100 grams of the compound. So for the moles of carbon, you're going to have 75.69 grams of carbon per 100 grams. And if you want to figure out how many moles that is, well, then let's multiply by 1 mole is going to be 12.01 grams. And we'll get an answer. It's how many moles of carbon there is. And with the aid of your trusty calculator, you will determine that this value would be 6.3 moles of carbon in 100 grams. So then we need to figure out the proportion to oxygen. So you take your 15.51, if my tool would write, would not be nice, grams of oxygen. And the molar mass of oxygen for one oxygen atom, this is not O2 now, is going to be 16, close enough to 16 grams per 1 mole. And you do the math and you'll see that it's just a little bit less than 1. It's kind of a fraction. 0.969 moles of oxygen for that number of moles of carbon we determined there. And then next we'll determine the moles of hydrogen using its percent. So apparently out of 100 grams you have 8.8 grams of hydrogen. And you'll take that times using divided by its, or the reciprocal of its molar mass, and that would be 1.00, oh, I'm at the bottom of the screen, shucks, grams per mole. And when you put that into your trusty calculator, because who's going to do that without it, we'll discern that this would be 8.73 moles of hydrogen. Well, that comes out to be a very funny looking set of values, doesn't it? But we're looking for the empirical value, or the empirical formula. So in the crudest sense, we have carbon at 6.3, hydrogen at 8.73, nasty looking, weird values, huh? And oxygen at 0.969. Now clearly this is not going to work because we want integers and whole number, close or smallest whole number ratios for an empirical formula. And if you think back to the example I showed you before, what shall we do next? The best strategy is then to take each of these coefficients and divide them by the smallest of the choices provided. So that would be this 0.969, and that will make oxygen come out to be the integer 1, and divide each of the other ones by 0.969 and determine what that gets you. Sometimes it'll get you the right spot, but sometimes it'll get you a lot closer, and then you'll see what to do. So the consequence of that little division exercise, if you divide 6.3 by 0.969, I got 6.5. The hydrogen divided that 8.73 by that value, I got 9. Oh, that's an integer. We like that. And oxygen as 1. Well, clearly we're not quite there yet because carbon is not an integer, but the other two are. And if you are good with fractions, let me try to clear up my drawing here. 6.5 can be doubled to get an integer. And so the better way of looking at this empirical formula would be put twice 6.5 is 13, twice 9 is 18, and twice of the oxygen 2 is going to be CO2. So C13H18O2 would be the empirical formula from this data. A little bit of math manipulation, but not awful. Now, the second part then is going to be to come up with the molar mass of the compound, get the molecular formula, given the molar mass as shown at 206.3. So we need to put that information together. To make it easier, we got to transcribe information from the previous slide. So the empirical formula turned out to be carbon 13, hydrogen 18, oxygen 2. Looks crazy, but who cares? What we have to do now then to come up with the molecular formula is determine whether the empirical formula is in fact the same as the molar mass or some fraction of it. So what we need to do is come up with the molar mass of this molar mass for this empirical formula. And so let's do the math. We don't even have to play sig figs in detail here because we'll be fine. So 13 times 12 is the amount of the mass for the carbon. 18 times 1 is close enough for hydrogen. And 2 times 16 for the oxygen. Put it in your calculator, think it through. This 13 times 12 is 156, 18, 32. And it all adds up to, well, guess what? It's 206. So the molecular formula then has the same molar mass as the empirical formula. So the empirical formula is the same as the molecular formula for this particular compound. It's not always true, but this case it is exactly the same because it's not the molar mass is not a multiple of the empirical formula. They are the same. All right. Now, let's see what other examples we can do with percent composition and empirical formulas. More examples are sometimes good. All right, so first we had ibuprofen. Now let's go to another over-the-counter medication, acetaminophen, also known as Tylenol, and see what we can talk about for percent composition. This shouldn't be tricky, but it's something worth talking through. And when we're talking about mass percent, we want to know how many grams out of 100 grams will be each of those elements. To begin with, you have to come up with a molar mass. So the molar mass of the compound is going to be 8 times 12, close enough for our sig figs here, for carbon, which is what, how much? For the carbon, right, is 96, plus 9 times 1 is the hydrogen, carbon, hydrogen, and nitrogen is just 14. Don't have to do any multipliers because there's only one. And 2 times 16 for the oxygen is 32. And writing them out this way has a purpose. By the time you add them all up, you'll get the molar mass for this sum of these elements combining to be 151. Check me with your math here. Grams per mole. And now what we're looking for is the mass percent for each of the elements in the compound. So start with carbon. So the percent of carbon becomes much straightforward once you see where we're going here. It's going to be 96 grams out of 151 in the formula. And put it in your calculator. Of course, we don't want to do these in our head. That'd be not necessary. So it's 63.6. The percent of hydrogen is going to be its number of grams out of that total in the molar mass. So it'll be 9 grams, essentially, out of 151 grams. And that fraction is much smaller, apparently, huh? And so instead of 60-something, it's going to be 5.96. I'm leaving it as a 3 sig fig answer for the moment. Oh, these are percents. Don't leave that out. Oh, times 100. I don't even write those in. I just do them mentally. Sorry about that. And then the, nitrogen, percent of nitrogen will be 14 grams out of 151 grams. And if you put in the calculator, this comes out to be 9.27%. Remember, you had to put in a times 100 for each of these to get a percent. And just as a reminder. And then the last one is the oxygen. The percent of oxygen will be 32 grams out of 151 grams. Times 100 gives us a percent. And the answer to that one turns out to be 21.2%. Now, if you've done these all right, all correctly, should add up to, and it does, 100%. So that's another example, not a complicated one, but maybe helpful about how we can use mass percent in understanding empirical formulas and compounds. I hope you find those helpful. Good luck on your homework. Ask more questions as needed, and see you in class. The next part will be a separate recording.